Hey guys, want to talk about astronomy here. We're going to look at the little stuff, the close stuff to us, like everything that's right around us, our sun and the planets around the sun and the moons and some of that information. And then next week we can look at stuff that's out beyond that. Okay, so this is called solar system astronomy, and the solar system um, is the sun, the planets, and anything that goes around the sun. The sun is the solar object that holds all that stuff in. Gravity is the force that pulls it. The sun has about 99% of the mass of the whole solar system, and then there's all this little stuff that goes around in circles around it. Now, this is the old system. We used to think that the Earth was in the middle of everything here, and the moon went around the earth. Well, that's correct, but we thought everything went around the earth. That's not an unreasonable assumption. The reason it's okay to kind of think about that is that when you get up in the morning, the sun comes up in the east and it goes over your head and it goes back down. It looks like it's going around you, right? Mars comes up in the east, goes down in the west. Jupiter and Saturn and all the planets and the moon and everything rises in the east and sets in the west. And so for a long time, here from 150 to about 1600, that was the prevailing model of how everything worked. And they only knew about Mercury, Venus, Mars, Jupiter, Saturn. Those are the only planets that you can see without a telescope. So up until the time that we actually built a telescope in the 1600s, then those were all the planets that we knew about, and they all appeared to come up and go down, and we were pretty comfortable with that. We knew there were stars. They knew that those were farther away than the planets, so they had this sphere of heaven that was even farther away. And this was just accepted dogma. The thing is, it works. You can kind of see when to plant your crops and when it's going to be summertime, and you can work out a whole system like this even though it's not technically right. Okay? So I'm not blaming them for believing this, but today we know a little bit better. And let me show you some of the reasons that we think this. Right here I have a picture called retrograde motion, and this is a particular thing that happens whenever there is a planet and you're watching this thing come up every day. Here it is at April 1st. May it's moved over to here, and when I say it's moved against it, we're looking at the same time every day, and it appears to move against the background of the stars. So April it's here, May it's here, and then it does this weird thing. I'm sorry, April's up here. Yeah, we're on the November track here. So November 1st, it would be about here. December 1st here, January, everything's moving in order. It's moving faster than the stars appear to move, but it keeps going the same way. But then it does this weird little loop backwards. And so February and March it's moving backwards. April it stops going backwards and starts moving forward. May and June would be down here. We refer to that as retrograde motion, where the planet is going one way and then it appears to go backwards the other way. And so they were trying to hold on to that geocentric, that model that explained the with the geo, the Earth in the center, or Ptolemaic system is another name for that. Ptolemy of Egypt cataloged the stars, and this was a system he came up with. And it kind of makes sense, but you start seeing little things like this, retrograde motion, where the planet is moving and then it flips around and goes back the other way. That's weird, right? So this guy, Kepler, in the 1600s came up with some mathematical formulas. All of the fixes that they had tried to do before had said, well, people had said, let's put the sun at the center, and the earth goes around the sun, and everything else goes around the sun except for our moon. The moon goes around us. But Kepler here worked out the mathematics of it. And what he had to do to make the math work was to say that orbits are ellipses. They're not perfect circles. Perfect circle won't work, but this flattened circle here, an ellipse, will work just fine. if you put the sun at one of the focus points, there's two little points right here, and you can actually get two thumbtacks and put it into a piece of cardboard and then a piece of string, a loop of string tied together. Put your pencil in that loop of string and move it around, constrained by the string and those two thumbtacks, and you'll draw an ellipse. The farther apart you put the thumbtacks, then the flatter the circle you get. The closer together they are, the more circular it becomes. If those two thumbtacks were at the same point, bam, it would be a perfect circle. But this flattened circle, this ellipse, works, and that's what Kepler was able to show mathematically. He was also able to show that planets sweep out equal areas in equal, should have the word time there. So if it took a month for a planet to move from here to here on that elliptical path around the sun, a different month's time, the same month's time, might get you from here to here, but you shade that green area, you shade the blue area, and mathematically you can show that those are the same area. They sweep out the equal area in the equal amount of time. What that means is that the planet is going pretty slow when it's out here far away, and then it speeds up as it gets closer to the sun, and then it's going to slow back down as it comes here. It's a little bit like if you're on your bike and you roll down a hill and then roll back up the other side. You're way far away from the source of gravity here from the sun, and you're kind of rolling down the hill, speeding up and up and up, and you're going faster and faster, and then you slow down as you come here because the gravity of the sun's trying to pull you backwards, right? But your momentum carries you forward around that circle. So you speed up, you're moving faster down here, but you're closer, so you've got that much area. Here you're moving slower, you don't go as far, but you're farther away, and the areas work out to be the same. His last rule here, the three laws of Kepler: when revolving around the sun, the square of the time divided by the distance, the cube of the distance, is the same for everything that's going around the sun. So if you take the time it takes the Earth and square that divided by the distance cubed, you get a number. If you take Jupiter's time squared over distance cubed, you get the same number. If you take Saturn and Uranus and Halley's Comet and asteroids and meteors and comets and anything that's going around the sun, you always get that same number. That's pretty neat that he was able to work that out before you could even go down to the store and buy a pencil, really. No calculators, no computers, just all in his head and on paper. Pretty neat. Anyway, here is a better picture of the way things actually work. You've got the sun in the middle, then you've got the planet Mercury is the closest, and Venus. Earth is third. We've got our moon that goes around us, and then you've got Mars and Jupiter and Saturn, and the stars are still much farther out away. Copernicus played a role in this. He published a book in the 1600s of the revolution of the planets or something like that. It was in Latin, De Revolutionibus Copernican, something, I don't know. I don't speak Latin. Anyway, that's called the heliocentric system, or the Copernican system. Helio would refer to the sun, and it's at the center of our solar system. This makes up the solar system. We've believed in this since the 1600s. We've sent spaceships out to Mars and Jupiter, and the old system wouldn't have worked. It wouldn't have gotten it there at the right time to meet it there and stuff. This is the right model, and it was a pretty big battle to change ideas. People don't like to change ideas, even when confronted with the truth. And this is a pretty good historical illustration of that. You're welcome to go read some more about that. Copernicus, just looking up Copernicus in Wikipedia would get you started on that, or Tycho Brahe or Kepler or something like that. Okay, this is a little animation of these two models. Over here you have the heliocentric model with the sun and all the planets, and the blue is the Earth there, and everything going around a nice orderly system with the sun, all that mass at the middle. Over here, though, you have the geocentric model, and you can start to see these loops upon the loops, those retrograde motions right there. That's what they had to do to make that work. And you see how complex that is. Generally in science, generally in real things, the simpler model is right. And so, that's you can argue for the geocentric model if you want, but that's what you're up against right there, and all those weird circles on circles, and it just gets more and more complex. We use a thing called Occam's razor to say, let's pick the simple solution because that's probably right. All right. So, thinking about motion. In that first picture there, you see the sun, you see the earth. The earth goes around the sun. That's referred to as revolution. It takes us about 365 days to go around the sun in that manner right there. So every year, every day on your birthday, every year on your birthday, you've made another trip around the sun. And that's pretty exciting. The radius of that circle, it's not quite a circle, it's an ellipse, but it's pretty close to a circle, is 93 million miles. So that's a big circle, and that's a big trip. We're moving pretty fast to do that. Rotation there is when the Earth spins on its axis. So here's the axis of the Earth, and you see that the Earth is spinning on that axis, and it takes 24 hours to do that. That causes the day. Every 24 hours we move into the sun's beams, the light, and then we rotate around and the sun is blocked by the earth. We're on the dark side of the earth, and that makes night. So that makes sense. First picture is a year, second picture is a day, and then there's this one other motion that isn't really important in the time frame of our lives, but there's a wobble to the axis's tilt. You know that the earth is tilted at about 23 degrees relative to the plane of the solar system, but there's a little wobble in that. It's almost like a top rotating. If you've seen a top spin, it kind of wobbles around. That's referred to as precession. Again, it takes 26,000 years for that to happen, to go around one time. So that's not going to change much in our lifetime. But if you go back and you look at the ancient pyramids that were built a couple thousand years ago, they are oriented toward the pole star. There's different stars that they were interested in, and those orientations no longer make sense because the Earth's wobble has changed that in the course of some thousand years. So those are the three forms of motion that we need to think about. We go around the sun every year, we spin on our axis every day, and then this thing, precession, you don't have to worry about it too much, but it does change over a long period of time. The Earth has this grid that we use to map places on the Earth, and you've heard about lines of latitude and lines of longitude. Latitude, there's an equator that runs straight across, and then there are lines that go up from that. Sometimes people use the word ladder, like you would climb a ladder. These look like the rungs of a ladder, so that's kind of a little mnemonic, a little memory device to help you keep all that straight. You've got the North Pole at the top, the South Pole at the bottom, and all these lines of latitude tell you where you are. It's Charlotte, North Carolina, Columbia. We're about 34, 35 degrees north of the equator. So here goes the equator. Each of these lines on this picture is 15 degrees, so there's 15, 30, and we would be a little bit above that second line above the equator there. So you could find that place. But there's lots of things at that same latitude right there. So we need something going the other way. We call those longitude lines. This is the Great Meridian there. It runs through a town called Greenwich in England. The reason it runs through there is because that's where the Royal Observatory is. That's where the astronomers were all sitting, and they said, well, why don't we start it right here? Okay? And there was something of a battle about that, too. The French thought they should have it. The Germans wanted it. Whatever. The British won. And that runs from the North Pole to the South Pole through Greenwich, England. But then we measure to the west of that and to the east of that. And you can see here to get to Charlotte, for example, you'd have to go 35 degrees north and 81 degrees west. So there's 15, 30, 45, 60, 75, and a little bit more. 35 degrees up would put us a little dot right there, and that would be Charlotte, North Carolina. New York is 40 degrees north, so you got to go farther north, but only 74 degrees, so a little bit east, and you could see that that would put us right there. Meanwhile, Paris, France, you got to go up 49 degrees and east of the Great Meridian there with 2.4 degrees, so we'd be about right there. Okay, just a little bit to the right of that line. All right. The reason I wanted to tell you about Earth's lines of latitude and longitude is because there's a similar thing in space that we use to map all of this stuff. And right here you can see that that little circle in the middle is Earth. It's got the North Pole, it's got the South Pole, it's got the equator running right there. Well, if you extend the North Pole out into space, then we call that the North Celestial Pole. If you extend the South Pole of the Earth through space, that would be the South Celestial Pole, and the whole sky is going to appear to spin as if it's on that same axis. Not because it's spinning, but because we're spinning. If you stand in a room and you just spin around in a circle, it looks like the room's going around you, and this is exactly the same thing that's happening here. We're spinning on Earth. It makes the stars appear to move around us. It makes the planets appear to move, the sun, all of that stuff. Okay. The equator of the Earth runs right there. You could extend that, kind of slice it with a plane across there, extend that out through space. You get something called the celestial equator, and then you could measure north or south of the celestial equator, and there is a line, and you could measure east or west of that. Okay, that's going to end up that's going to result in a grid like you see right here. So we're standing on Earth, and here they're looking south. The west is on our right hand, the east is on our left hand, north is behind us, and we're looking up at the night sky. It's going to rise in the east, and it's going to go down in the west, and we can map right there runs 0 degrees. That would be the celestial equator, and there are certain stars, certain constellations on that line, and then 15 degrees up and 30 degrees up, 45, and then we could go either instead of degrees of longitude, the vertical lines, we're mapping hours of right ascension. So here's 0 hours. That's kind of the starting point. 1 hour, 2 hours, 3 hours, 4 hours. There's subdivisions too that aren't on here, but it comes back around to 24 hours. Here would be 22 hours, 23 hours, and you're back to 24 hours. So one day the whole thing spins around. You can see that it's going to spin from 0 to 1. 1's going to move in front of us. 2's going to move in front of us as it moves that way. All right. Straight over your head is a point called the zenith. Straight below your feet would be a point called the nadir, N-A-D-I-R. That's not really important, but sometimes you'll hear people talk about that. But can you see why there are certain stars that we can't see? It's because they're down below our feet. The Earth is blocking it. I can't see the star or the constellation that's right here or here or here unless it just happens to rotate up into my sky. Now, if I went a little farther south, if I went to Brazil, there would be different stars that I could see, different constellations. And so your point on Earth makes a big difference on what you actually see. But that grid system works really nicely. Here's a picture of the solar system. You can see we've got the sun in the middle. It's a giant ball of gas, the plasma, if you will, that is undergoing fusion. And we'll talk more about stars later and how they work and stuff. You can say it's gas that's burning, but that's not technically true. It's really hydrogen that's getting mashed by extreme pressure and heat into helium and into heavier atoms. And that gives off a tremendous amount of light and heat that you see. Mercury is the next planet, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. When I went to school, we talked about Pluto being a planet, and that's not necessarily the case anymore, or maybe it is, maybe it isn't. That's still kind of a topic for debate. The reason it's in question, though, is because we built bigger telescopes and we found more stuff. So we kind of either need to count all that other stuff or we need to stop counting Pluto. So I'll tell you more about that later. But there's some other things in the solar system, asteroids and comets, all of that stuff, and any moons around any of our moon. Jupiter has 80, 90 moons. Saturn's got a mess of them. All of that is what we mean when we say the solar system. Anything that goes around the soul, around the sun. Okay? Sol is another name for the sun. S-O-L. So let's kind of talk about each of these real quick. Here is a picture of the sun. You can see the diameter is huge right there, 1.4 million kilometers. It's 155 times bigger than Earth. If you put Earth's across here, not around the surface, but just straight line diameter, you'd take 155 Earths to cross the center of the sun. Okay, that's crazy. The mass is 2 times 10 to the 30 kilograms. It's 335,000 times more massive than our little dinky planet. The surface temperature is about 10,000 degrees Fahrenheit, but down in the core is super hot. And again, that's because of all that heat and pressure there that is changing hydrogen into helium, and that releases tremendous heat and light. That light is coming out everywhere, but sometimes there's a little brighter spot or a dimmer spot. Sometimes you get these CMEs, these coronal mass ejections and flares and all sorts of things. But the sun is a really interesting place. You don't want to be there. It's a little too hot. But we have observatories set up on Earth and out in space watching the sun and checking it out. We would die without the sun, so we're pretty grateful to have it. And here's a little bit of the inside stuff. You can see the layers here. On the outside, you have this chromosphere right here. So that's your outer layer. Can you see how it's all swirly and it's almost like Jupiter has those clouds and those storms raging and stuff. Once you go inside the chromosphere, you're down to the photosphere, and that's going to work its way here into the convective zone and the radiative zone and the core down in the middle. That's where that hydrogen fusion is happening, and where it's, I think it was, 28 million degrees or something crazy. And then that energy is going to work its way, radiate through this region. You've got convection going on here, and that's causing a lot of that stirring in clouds and storms and ripple effect on the surface. You do have some cooler spots here referred to as sunspots. So they're not as bright as the rest of it. Those are really interesting. I've got a slide about that in the middle. What else you got? Little filaments or little squiggles of colder, relatively. Maybe it's only 8,000 degrees instead of 10,000 degrees like the rest of it, right? Here's a flare. You've got all this pressure pushing, and sometimes you get that flare, that prominence, a coronal mass ejection coming out. So a lot going on there with the sun. Let me tell you about the sunspots. Over here on the side, you've got a little video of this thing of the sun rotating. And yes, the sun does rotate. It takes about 10 hours to spin on its axis. Everything is moving, and the sun is no exception here. But you can see those sunspots going by, those little dark spots. And you can see that if we drew the equator of the sun in, it would kind of go here. And so there's kind of matched pairs above and below that center line of the sun there. And that's kind of interesting how that happens. We don't understand everything about the sun, but we've been watching it for a long time, those sunspots. And back in the 1870s, they reported this many, and in the 1880s, they wrote down the ones. And can you see how they start above 30 degrees, above and below the equator, and over the course of about 11 years, work their way to the equator, and then they pop up 30 above and below again. And so you get that pattern right there with matched pairs starting above and below and coming down to the equator. That's kind of neat. There's something going on inside the sun that every 11 years you get this thing happening where the sunspots kind of start over. Down here, you actually have the area, how much of the sun is blocked. So it starts out not a whole lot, and over that course of 11 years, it gets stronger and then down. And it goes up and down and up and down. We like looking for patterns because it tells us something about what's going on here. That pattern kind of got stronger, and now it's kind of falling off again. So there's another pattern that we could be looking for. You can see that up here. It wasn't particularly bright, the more red and yellow and black that you have, but look at that, it gets more, and then it starts falling off again. Right matching up with this peak right here. So lots of interesting things about sunspots, and check that out if you're interested. Earth is the planet that we know best, so I wanted to talk about that first. You can see the numbers here. I don't expect you to memorize all these numbers and stuff, but just kind of for reference, as we talk about the other planets, Earth has a mass of 6 times 10 to the 24 kilograms. That's a 6 with 24 zeros after it. It's pretty massive, but remember that the sun was 2 times 10 to the 30, like a million times more, right? Not quite a million, but I think it was 335, whatever. The diameter is listed there, about 12,800 kilometers across. The density is an important number. I want you to watch that. 5,500 kilograms. Escape velocity says how fast do you have to go to get off of the surface. So when we shoot a rocket into space, that's how fast it's got to go. Otherwise, it gets pulled back down to Earth. The distance from the sun. This is an important number, and it's expressed here 2 different ways. One is 1 AU, 1 astronomical unit. An astronomical unit is defined to be the distance from the sun to the Earth. Okay? We're the ones that set it up. We got to pick, right? And we said our distance from the sun is 1 AU. That works out to about 150 million kilometers. All right? So remember that number, and as we look at the other planets, we can go, well, they're 2 AU, they're twice as far away, or 3 AU, or half an AU, they're half of our distance. So it's kind of a handy yardstick to have. The rotation period, we've talked about that. It's 1 day to spin on our axis. The revolution period would be how long does it take to go around the sun? 365 and a little bit more Earth days. That little bit more is the reason that we add a leap day every 4th year, right? We add 1 day to the calendar in February, the 29th of February, and we do it every 4th year to kind of fix this. It's a little bit longer than 365 days. The axis is tilted 23 degrees over. The average temperature is something like 46 degrees Fahrenheit, but can go anywhere from 120 degrees Fahrenheit out in the deserts, and I hope Columbia gets up close to that, but not quite that high. It goes down to negative 40 degrees. So I think they just averaged those 2 numbers. It wouldn't quite do it. That would be 160, which would be 80. I don't know what they did. Mean surface temperature, I guess they're saying you take the temperature in all the different places. That's about what it is. Anyway, the highest point's Mount Everest. Believe it or not, that is not the highest mountain in the solar system. We do have a fairly heavy atmosphere, dense atmosphere, lots of gas. It's 78% nitrogen, 21% oxygen, and then a little bit of everything else. We saw those numbers back when we talked about meteorology as well, so you're familiar with that. But the atmosphere is immensely important in all this. We have 1 moon, okay? So that's the data on Earth. We know how Earth works and are kind of comfortable with that. Let's go look at some of the other stuff in the solar system. Before we do that, we want to look at our moon because that's kind of part of the Earth system as well. But the moon is right here. It's about 225,000 miles from us. So it moves in an elliptical orbit, mostly circular orbit, at a pretty good distance out there. Its day is 27 of our days. So it takes 27 days to turn on its axis. That rotation, that moon rotation, is so slow that if you look down here, it's not on here, but the time it takes to move around the Earth is about that same time. And what that means is that we're always looking at the same side of the moon. It's tidally locked, and any moon that's in a tidally locked orbit means that the same side always faces the planet, even as it moves around us. It's about 2,000 miles across, or through the middle, you know. The mass is given there, the surface temperature. Check it out. Negative 244,000 degrees, not thousand, negative 244 degrees Fahrenheit, up to positive 273 degrees Fahrenheit. It's much colder on the moon than we get here, and it's much hotter on the moon than we get here. What's the difference? Well, one side of the moon is facing the sun, and the other side is not. That's going to change over the course of that 27, 28 days. But basically, if you're on the sun side, if you're in the sunlight on the moon, you're pretty hot. It's 273 degrees. That's why the astronauts had to have the big spacesuits and the air conditioners in the spacesuits and everything just to survive. Meanwhile, if you're in the dark, the nighttime of moon is mighty, mighty cold, and you're going to need an extra blanket. So be ready if you go up there. The gravity is 0.1667 of our gravity. It's about a sixth of what it is here on Earth. So basically, if you weighed, say, 180 here on Earth, and you went to the moon, you would have a weight of 30 pounds. That's a great weight loss plan, right? You've seen the astronauts bouncing around on the surface of the moon like little kids, like they're on a trampoline or something. Gravity is not pulling down as hard. Why? Because the mass is so much smaller. And gravity is tied up with how much mass there is in both objects. And you've got so much less mass, you're going to have less gravity. If you got in your car, tried to drive to the moon, that's not going to work out very well. But if you could, it would take you about 135 days to get there. In a rocket, it takes 65 hours. So that's kind of interesting. That's about, what, 3 days, something? And that's how far the astronauts traveled out there and back in their little tin can. We've sent 12 astronauts up there to walk on the moon. There were a couple extra that stayed in the capsule and went around and around while the other guys got to go down to the moon. But, you know, that's not a whole lot of people. They brought back a bunch of rocks. You've got craters. You can see these little marks right there. That's where something has come in and impacted, has hit the moon. And some of those are 140 miles across and 15,000 feet deep, about 3 miles deep. There are mountains that are about 16,000 feet. That's not as big as on the Earth, that we have bigger mountains than they do. But the moon's an interesting place. It gets very hot, very cold. Didn't say anything about this. The reason it's so hot and so cold is that there's no atmosphere. There's no air to kind of serve as a blanket to hold that heat that comes in, and then to keep us warm during the nighttime. Our atmosphere here on Earth does that. The sunlight warms up the atmosphere, and that gas holds it. There's no gas on the moon. There's no atmosphere. So that's another hindrance to trying to live there. Nothing to breathe, very hot or very cold. You can't go to Walmart and get anything. I'm not sure I'm interested in going, but thanks anyway. Now, the moon phases are pretty interesting, but they're really simple when you draw the right picture. The moon is going to change its appearance over the course of that month. It takes about 28 days to go around, and as the moon goes around the Earth, right here, the sun's on one side, the sunlight is going to light up the side that is facing the sun. So if the sun's right here, it's going to light up this side. And then when the moon moves a little farther around, it's going to light up the side that's facing the sun. All the way around, you can see that the right-hand side of the moon is lit up and the left-hand side is dark because it's away from the sun. Okay? Now, we're here on Earth. We're looking out, and when I look when the moon's right here, I see the whole face of the moon lit up. We call that full moon. The full moon shows us the whole circle there. When I look when the moon's over here, you can see that this side is dark and that side is light. Now, if I'm standing there looking out, my right-hand side would have a dark place because I'm seeing part of the moon that's not lit up, or I'm not seeing it because it's dark, but it's still there, right? Meanwhile, the left hand would be here. And you can follow all the way around. If I were to stand here on the earth and look when the moon is right there, again, my right hand is dark, the left-hand side of the moon is lit up because the sun's coming from over here, and it would look like this right here. On the left is light, on the right is dark. That would be a quarter moon right there. And from the full moon, it wanes. That waning is when it's taking away light. We're seeing the dark part get bigger and bigger, or we're seeing the light part get smaller and smaller. When the moon is right here and I look at it, it's the far side of the moon that's lit up, and I'm looking at the dark side. So we would call that a new moon. And you either can't see it like right there. Right here, it's waxing. It's getting brighter and brighter. It gets all the way up to the full moon. And then it begins to wane from the other side. So the moon still goes out there, but that's in the shadow caused by the sunlight falling on that side, not on that side. So that's the picture that we have. New moon, it waxes to a crescent moon, to a quarter moon, to a gibbous moon, to the full moon, and then it wanes down the other way. So that's kind of neat to watch over the course of a month, or even a little bit less than a month. It's going to do that every time, go through the full cycle there. Here is our first planet out from the sun. Wanted to do Earth and Moon first, but we're looking at the numbers here of Mercury. And let me just point out some of these. It is smaller than Earth. It is less massive than Earth. We had 12,000 here. It's only 4,000. And our mass was 6 times 10 to the 24th. So this is like 5% of our mass or something. But the density is about the same. Earth is a rocky planet. Mercury is a rocky planet. Okay? So if we went and stood on Mercury, it would be very much like we are. It's much closer than we are. These numbers are interesting. The year on Mercury, it takes 88 days to go around the sun, but it takes 59 days to spin on its axis. It's not quite tidally locked, but it's getting close. And the sun would almost, not quite, but it's seeing a very slow rotation there, almost seeing the same side all the same time. It's not tilted at all, 0 degrees. We're tilted 23. It is up out of the plane of the solar system, so it's a little bit above and then would go below. It's not quite on that flat disk that we think of with the solar system. If you drew a line from the sun to us, this would be a little bit above that line and then go a little bit below. The eccentricity, that's how flattened the pattern is, the path there. It's about 0.2, which is a little bit flat. Okay, that's getting elliptical there. Surface temperature, 800 to negative 280. You're really close to the sun. You're the first planet. But when you see that big wide swing like that, it's a pretty sure sign that there's no atmosphere. And indeed, when we get down here to the atmosphere, it's just a little bit of hydrogen, a little bit of helium. Everything else has been blasted off by the sun's radiation. It's gotten enough energy from the sun just to send it elsewhere. Okay, so here's kind of an average surface temperature there. But again, if you're facing the sun, it's going to be super hot, and if you're on the dark side, it's going to be super, super cold. Not a very hospitable place. No air. It's kind of like the moon, only worse, maybe. And here's Venus. When you look at Venus, it's covered by heavy clouds. Venus has got a killer atmosphere. Okay, it's a super thick atmosphere. unfortunately, it is a killer atmosphere. It's 96% carbon dioxide, a little bit of nitrogen, almost no water. Okay? We can't breathe there. All right? Good reason not to go. Here's another good reason to go. 847 degrees Fahrenheit. That one's pretty even. It doesn't have that wide swing from hot to cold um, because it's got that heavy atmosphere and it's carbon dioxide, which is really good at holding in heat. So the sun's energy comes in and it stays there. It's super hot. You could drop lead on the surface and it just melt. Okay, that's crazy. Um, it's about the same size as the Earth. Remember, we were 12,700? It's 12,100. So sometimes Venus is called a sister planet to us because it's kind of the same size, because it has an atmosphere with clouds. If you use radar and scan the surface, we've sent a spaceship up there and scan the surface through the clouds. That radar comes back up and shows that there are mountains and there are craters and there are valleys and things that we're used to seeing here on Earth. But it's 243 days to spin on its axis. It's 224 days to go around the Earth. So there again is something that's almost tidally locked. The day is actually longer than the year on Venus. So that's kind of weird. Here's another weird thing. The tilt of the axis is 178 degrees. So it actually spins the opposite direction of almost everything in the solar system, certainly Earth. Where our sun would come up in the east and go in the west, it would come up in the west and it's rotating the opposite direction. Most people think that that's because some kind of large object, asteroid or something, collided with it and kind of spun the whole thing upside down. It would have started out the right way and then got turned. We've been hit by asteroids a bunch, and that's probably the source of our 23-degree tilt. But I've got a picture here coming up with the tilt of all the planets, and you can see what they are. Anyway, that's a little bit about Venus there. Don't need you to know the numbers, but what about the density? That would be one more. Remember, Mercury was 5,000 something. We're 6,000 something. It's 5,000 something. Venus is a rocky planet. You could go stand on it. You're going to melt, but that's a different problem, right? All right, Mercury, Venus. You've got Earth. We've already done that. Here's the first planet outside of Earth. Is it a rock? My density is about 4,000. It's not as much as Earth or Mercury or Venus, but it's still a rocky planet. You can go stand on Mars. We've got little rovers that are driving around on Mars. We've dropped in some, a little car that drives around and takes pictures and has a drill, and they can test the geology, the rocks and the stuff, and send all that information back. So definitely a rocky planet there. The distance from the sun, 1.5 AU. It's about 1.5 times as far as we are from the sun. So it's farther out there. The rotational period is 1 day. It's got about the same length day as we do, a little bit longer. The year, though, it's getting close to 2 years to go all the way around the sun. So you would be half your age if you lived on Mars. The tilt is very similar. We're 23, they're 25 degrees. The orbit inclination, it's a little bit above and below. The surface temperature, though, negative 190 to 100 degrees. Hot on the sun side, cold on the dark side, right? Probably not as much atmosphere as we have. But what is there? Again, it's carbon dioxide, a little bit of nitrogen and argon. Mars has 2 moons. We're the first planet to have any. We have 1. Mars has 2. And it's an interesting place. Don't want to go there, but that would work. It does have this huge canyon, this huge running through it. That's I don't know, the size of North America or something. I mean, it's just this huge thing with this cut across the surface, big scar. It also has a mountain that's 3 times taller than Mount Everest. So Again, it's about half of our diameter, but that mountain is a lot taller than anything that we've got. That's actually the highest mountain in the solar system right there, Olympus Mons. So let's step out to Jupiter. And the first thing I'd like you to look at is the density here. Everything else that we've seen is between 4 and 6,000. Jupiter has a density of 1,000, 1,314 kilograms per cubic meter. Okay, that's radically different. Jupiter is radically different. It is what we call a gas giant. There is no rocky surface to go stand on. We can't drive a car around on Jupiter. We would just keep sinking into this gas ball. It's a big ball of gas, kind of like the sun is a big ball of gas. Jupiter is not a star because it doesn't have enough mass. So if you remember, the sun had a mass of 2 times 10 to the 30 kilograms. This is 1,000th of that. And that's not enough mass to get fusion going. You've got to have more pressure, more weight of all of that pushing down. But if Jupiter had been 1,000 times heavier, it could have been a star too. Okay, there are lots of solar systems out there that have 2 stars in, that go around, and there's nothing unusual about that. Maybe something like half of the solar systems have multiple stars, 2 or 3 stars. We only have 1. Jupiter would have been a contender if it had more gas to work with. But it is mostly hydrogen, 90% hydrogen, 10% helium, a little bit of methane. Okay, we're not breathing there. It's 120 degrees, but that's in Kelvin. So that's like negative 173 degrees Celsius. It's cold, all right? You don't want to go out there. It's so far from the sun that it's just not getting enough energy to keep it at a temperature that we're comfortable at. A little bit of tilt. Takes 12 years to go around the sun if you're on Jupiter, and it spins in 10 hours. So here's this crazy big ball of gas, but it only takes 10 hours to spin on its axis. That's nuts. How far away is it? It's 5.2 AU. It's 5 times farther away from the sun than we are. All right, and so there's a little bit about Jupiter. We think of Saturn as having the ring system, and you can see the rings there. There's a planet, and then you've got all this stuff right there. The rings are about 270,000 kilometers in diameter. They're about 300 meters thick, so it's a real thin disk going. It's only 3 football fields thick from top to bottom. The particles are anywhere from a centimeter size, a little pebble, up to something about the size of a house. They are made of ice and silicates, minerals, and carbon, stuff like that. So Saturn is the planet that we think about as having a ring system. Turns out Jupiter has a little faint rock ring as well. Okay, and so that seems to be something interesting. I think the ring systems are neat because it's that same model of here's a big chunky thing with all this stuff going around in a flat disk. It's the same picture as here's the sun, and here's all of the planets and stars, not stars, the sun, here's all the planets, the whole solar system out here spinning in a flat disk around the sun, okay? So this is kind of like a little model of the solar system, big chunky thing in the middle, stuff going around in a flat disk. When you step out beyond the solar system, we are in a galaxy, and it's the same model again. You've got not a planet, not a star, you've got a black hole here, and billions of solar systems going around that. So that pattern kind of repeats as you get going bigger and bigger, and I think that's kind of neat. Even Earth is a little bit like that, right? You've got Earth in the middle, and the moon is going around in a flat disk. So that pattern of tells us something about how all this got created. Let's run through the numbers real quick. Yeah, it's big, it's heavy. Density, 690 kilograms. We were 6,000, Okay, Saturn is not a rocky planet. It's not even as dense as Jupiter is. If you the density of water is 1,000 kilograms per cubic meter. If you could find a big enough bathtub, you could throw Saturn into that bathtub and it would float. Okay, it would float in water. It's less dense than water. That's crazy. 9.5 times farther from the sun than we are. Spins in 10 hours, a 10-hour day. It's 29 Earth years to go around the sun. I wouldn't even be 2 years old there, right? So pretty tilted orbit, very cold. You know, when you're 9.5 times away from the sun than we are, you're not getting a whole lot of sunlight, and but you can see it's hydrogen and helium too. It's a gas giant. It's got enough gravity where it's pulled together some hydrogen and some helium that's been cast off by the sun, and it's good to go. 33 moons. I don't think I told you about Jupiter here. The number here is 60 moons. I think that's too small. Every time we build a bigger telescope or go out there, we find more stuff. So these numbers change as we learn more. But Saturn's pretty interesting. You can see this in a telescope, even if you get just a pair of binoculars or a pretty simple telescope. You can see Saturn and the rings of Saturn. That's kind of neat. With a pretty simple telescope, you can see Jupiter and 4 of its moons, called the Galilean moons. And can't see all 60 moons, but those 4 are pretty easy to see. And that's what Galileo was looking at. And it's one of the things that convinced people that the Earth wasn't in the center, because Galileo looked, there was Jupiter, and it had these 4 little dots, and sometimes there'd be 2 on one side and 2 on the other, sometimes it'd be 3 on one side and 1 on the other, and he realized that they were actually moons going around Jupiter, therefore not everything went around the Earth, okay? Because here's something that's going around Jupiter. Big deal. He got in big trouble for that, but he was right. Uranus here is the next planet out, and it's big, it's heavy, but the density here, 1,300 kilograms per cubic meter. Definitely a gas giant. This would not float. It's more than density of water, but it's 19 times farther away than we are. It spends 0.72 Earth days. I guess that'd be what, like 16 hours or something on its axis. 84 years to go around the sun. Really cold, lots of hydrogen, helium, 20 moons, faint rock ring system. It's so faint you can't even really see it here. But there is, in our passages by it and telescope work, we work it out, pick it out. Okay. Neptune is the last gas giant here, and there's the numbers on it. 1,600 kilograms per cubic meter, 30 times our distance from the sun, 19 hours to spin, 165 years to go around the sun. Okay, you wouldn't even make it to your first birthday, right? It's tilted above and below the axis, above and below the plane of the solar system. Cold, hydrogen, helium, 8 moons, little bitty ring system. Okay. So those gas giants are all the same. The rocky planets, Mercury, Venus, Earth, and Mars, are all the same. We got 4 rocky planets, 4 gas giants, and then there's this guy called Pluto here. I used to say Pluto right there. I don't know what happened. But it's a little thing, and the density is 2,000, okay? Which isn't a gas giant, but it's not quite a rocky planet either, right? So it's really kind of this weirdo. 40 times farther away from the sun than we are. 6 days to spin, and it's going backwards. It's 248 days for a, I don't think that's right. 240. Yeah, I think that's supposed to say years right there. It can't be 247 days. That's not right. Okay, it should say years right there. Tilt. Pretty tilted, and what else is interesting here about it? Very cold. That's not a surprise. It's so far out there. It's made out of rock and maybe some methane ice, and that's why it's not quite a rock giant. It's got all this ice frozen in there. It says here 1 moon. We're actually up to 5 moons on Pluto. But it's just really weird. This eccentricity is 0.25. That's really weird. Everything else is 0.01 to 0.09. Mercury's a little bit wobbly, but a little bit flat and circle. But Pluto here is really wonky. So it's kind of swooping in and back out. It actually crosses the orbit of Neptune. No, I'm sorry. Here's Neptune. Yeah, of Neptune. And so that kind of started this whole thing going on. Well, what's up with Pluto? It doesn't make any sense. It's not a rock. It's not a gas ball. It's orbit's really weird. All this weird stuff. And then we started. I'm sorry, this isn't where I wanted to go. Where am I? Right here. With Pluto, this is kind of a model of Pluto here. You can see the Earth is much bigger, and the Earth's not big for stuff, right? Here's our moon. Pluto's about the same size as our moon. It's actually smaller than our moon. And then we built better telescopes and better mathematical models, better computer simulations, and we started finding all of this other stuff. And here's a thing, Eris, that's right at the same size as Pluto. So if we're going to count Pluto as a planet, then we also need to call Eris and maybe Haumea and Maki. Where do we cut it off, right? So, but definitely Eris here is, Eris was the god of contention. And they named it that because they knew it would be a big deal and cause a big stink, because here's something the same size as Pluto, right? So it should be a planet, or Pluto shouldn't be a planet. And for that reason, Pluto kind of got demoted into a dwarf planet status here, where it's not a full proper planet. It does have spherical nature. It's got enough gravity to pull everything into a nice circular ball, but it can't clear its orbit. If it runs into Neptune, Neptune wins. Okay? All of these other things are also dwarf planets. We're finding more and more of those. But this little picture kind of hopefully illustrates the whole conundrum there. When I went to school, Pluto was a planet. Now we consider it a dwarf planet along with all this other stuff. And that's probably the best way to think of it. So that's Pluto. Right here I've got some size comparison pictures, and then down at the bottom the axis tilt. So looking real quick at that, you can see here's Mercury, that little dot, and Venus is bigger. Here's Earth. Venus and Earth are about the same size. I think they've got a little chunk there for the moon. Can't really see. Mars is smaller, but Jupiter, great big ball of gas. Saturn with its disk system, great big ball of gas. Here's Uranus and Neptune. Out farther, you got Pluto and some of these other trans-Neptunian objects, or dwarf planets, or whatever you want to call them, Kuiper Belt objects. The Kuiper Belt is a big band that runs out here. But in the background, you can see the sun. And that kind of brings it home that the sun is just huge, even compared to Jupiter, especially compared to Earth and some of these little guys. But on the other hand, the sun is right here, and there's Sirius and Pollux and Rigel and Betelgeuse and Antares. The sun is not a big star as stars go. It's definitely the biggest thing in our solar system. But when you look at some of the other stars, the sun is really a pipsqueak. You can see there's different colors of stars, red and orange and blue. There's green stars, yellow stars. Our sun is a yellow star. That color tells us the temperature of that star. The temperature tells us some interesting stuff about what's going on, how much fusion is still happening. And stars toward the end of their life tend to go red because they've cooled off. They're not as bright as a yellow star. If you think about turning on the eye of your stove, it's kind of a dull gray, and then it's going to go through a red and an orange, and I don't know if it'll get up to a yellow or not, but that brighter color indicates a hotter temperature. And it's the same way with the stars here. Down here at the bottom, we've got the pictures of the sun, the whole solar system there, including Pluto, and you can see the spin on all that thing. Mercury spins this way, Earth spins this way, Mars spins that way, Jupiter, Saturn. Uranus does, but it's tilted over. Neptune does. Pluto's backwards, and Venus is backwards. Well, Pluto's kind of out of whack so much that you can't see what it's doing. But again, I believe all of those started out straight up, and then some kind of impact with an asteroid or something tilted it and gave it the tilt of the Earth. All of these would have precession, would have a little wobble. Ours is doing the wobble there. Mars has got about the same thing going on, and so that's all of those. All right. Here's a table with all of this. I'll try to make that available to you if you are interested in it. But you can just kind of read across on the densities, for example, 5,000, 5,000, 5,000, 3,000 for the moon and Mars. All of those things are rocky surfaces. Then here's our 4 gas giants, Jupiter, Saturn, Uranus, and Neptune. Here's Pluto. I think it said 2,000 on the other slide. Looks like it's down to 18. So then maybe there's more methane, more ice. It's so far away, we're still trying to learn about Pluto. Okay, we're still trying to learn about Earth, right? But especially out there. The gravity is interesting. We're at 9.8 meters per second squared. And so you can see Mercury, you'd be super lightweight. Venus, you'd be close to our gravity here, 8.9 instead of 9.8. That's because the mass is similar right there, but Mercury is so much lighter than those other guys. The moon, we've already talked about that being a really lightweight. Instead of 9.8 is 1.6, and you can see it all the way across there. But look at Jupiter. If you go to Jupiter, you're going to weigh 23 times what you do here on Earth. Okay? It's because it's so massive. And that's where you don't want to go if you're trying to lose weight, all right? The escape velocities are there. The moon's pretty easy to get off of because it's so small, right? Pluto would be even easier. You only have to go 1.3 kilometers per second. The rotational periods here got a negative sign because that one's backwards. Same with Uranus there. Earth is about 24 hours. Moon, all those, we've seen those. Perihelion is the closest we come to the sun. So like Mercury, for example, would be 46 times 10 to the 6, or 46 million kilometers from the sun at its closest point, and 69 million kilometers at aphelion, the farthest from the sun. Look at Earth, though. We're 147, 152. Not quite the same number, but almost. And that means that we're moving in pretty much a perfect circle. This number down here, eccentricity, is a indicator of that as well. The smaller the number, the more perfect the circle is. So Venus is almost dead on a circle, and we're pretty close to that. And everybody else is 0.05, 0.02, something. Mercury has got an elliptical flattened orbit, and Pluto over here 0.24, like that. We've talked about the tilt, the temperatures, and all of that. The number of moons, we've got 1. Mars has 2. Jupiter, this has 79. Saturn 82. Again, these numbers change as we build more stuff. Pluto's got 5. Okay, the ring system, all of the gas giants have a ring system. Is there a magnetic field? Well, the Earth definitely does. Venus does not. The moon does not. Mars does not. They're geologically dead. There's no lava that's circulating in the bottom in the core to stir up that magnetic field and generate that magnetic field there. Okay, so just some stuff about that, all in one sheet there. We've already looked at this. Jupiter's huge compared to Earth. Earth is pretty big compared to Pluto. Moon is about the same as Pluto. All these guys are little. When do we stop calling them planets? We got comets in the solar system. These are objects that go around the sun. It's like a big dirty snowball, kind of a lot of ice, a lot of dust. There's a little bit of rock, and as they come close to the sun, they start to melt and gives off some gas that goes behind as a tail there. Here's a little animation that comet's way out in space. Look how eccentric that orbit is. And then it's going to swoop in close to Earth. You can see its speed up there, kind of like rolling down a hill, getting faster and faster, rolling back up the hill, slowing down, and going through that orbit again. Halley's Comet is a perfect example of that. It comes around every 86, 87 years. I think the next time is in 2040 or something like that. 2060 maybe. I can't remember. It came around in the 80s when I was in middle school, and wasn't quite as big and pretty as people were hoping. But comets are neat, and we actually have sent spaceships and impacted. We fired a gun at one of these things, shot off a piece and then smashed it into it, and analyzed the spray and the ice and stuff. So we're learning more about comets. We've got asteroids. If you look out through the solar system, you've got the sun and Mercury and Venus. Here's Earth, here's Mars and Jupiter. But between Mars and Jupiter, there's a band that we call the asteroid belt. And it's just a whole bunch of big lumpy rocks. Okay? Possibility A is these are things that were grabbed by gravity. The sun's gravity just kind of said, yeah, y'all go spin around me out there. Okay? They were captured. Possibility B is there was some kind of planet that got smashed, and this is the remnants of that. And possibility C is that these are leftover pieces that didn't quite make it into a planet. They didn't have enough mass. They weren't collected together and turned into a planet. So they're just kind of leftover pieces. But the asteroids are kind of neat. Not a whole lot to say about them. There is some interest in going out there and mining the asteroids. There would be a whole lot of minerals and things that we could use to make stuff. It could kind of upend the whole financial system here. If all of a sudden somebody had all of these resources that nobody else did, then that would kind of be kind of like people with lots of diamonds or lots of gold, or something kind of get to run everything. Well, if somebody goes out there and gets a whole bunch of asteroid material and that's a valuable commodity, then they've got the ball. So I don't know what'll happen with that. There are meteors. These are chunks that go around the sun, and if we cross into their path, then our gravity will pull them down through our atmosphere. There will be a lot of friction as they come through that, as they rub on a lot of air resistance right there. They get hot, they burn. If you've seen a meteor trail or meteor storm, you see little streaks of light, little, oh man, I lost the other word, falling star. It's not really a falling star. It's really a chunk of rock or ice or something that has come from a comet or an asteroid or a little piece of debris out there in space that is falling through our atmosphere, and the air resistance makes it super hot and it burns up typically. If it's small enough, it just burns up and never hits the ground. If it does hit the ground, it makes a crater, and this is a pretty big crater out in New Mexico. I believe you can see the road going to the edge of it, and there's a little museum built right there, and you can go look down in the hole here. Now, that's a pretty big hole, right? That's a meteor strike here on Earth, and at the instant that it hits the ground, it's no longer a meteor. Now it's a meteorite. But whatever, it's a chunk of something that fell out of space. You can see different meteor strikes here. There's nothing unusual about it at all. The Gulf of Mexico was probably a meteor strike right there and created a low place in the water, filled it in. But the moon is cratered. All the planets, all the rocky planets are cratered. Mercury, Venus, Mars, they all have craters. So it's no big surprise here that we've been hit in the past and continue to be hit by things coming down out of the sky. There's a lot of junk, not as much as there used to be, though. Back in the formation days of the solar system, everything was more chaotic and there was more stuff flying around. A lot of it's been scooped up now into ring systems and already hit the ground and stuff. Of course, something like 3/4 of the planet is ocean, so most of these just fall into the ocean and not a big deal. But sometimes they come down and hit on land. Okay. I think this is the last slide here. These are meteorites. These are things that have hit the Earth and landed here. And there's actually a market for these. There's people that go, and hunt these things down and put them on eBay and sell them. You can go buy meteorites, and they'll slice them and they'll make them into rings and different stuff. But you've got different kinds of asteroids here: Type C, Type M, Type S. You get different kinds of meteorites depending on if it came from the core or the mantle of, if it's solid rock, if it's still kind of molten, and then its path through the atmosphere changes it as well. It can crystallize structures and get these chondrites and stuff. Okay, so it's a meteor until it hits the Earth. At that point, it becomes a meteorite, and somebody's going to try to sell it. So, yep, that's it. All right, thanks for indulging me here. Let me talk about astronomy a little bit. It's neat stuff. This is all the solar system stuff, things that are close to the Earth. Next time we'll look at things that are farther out, beyond the solar system. And thanks for stopping by. Have a great day.